In this video, we are going to look at organic synthesis. This is the process of making organic compounds from simpler materials. So, key point, it involves breaking bonds and making new bonds. A key word that will come up here is target molecule, and this is the molecule that is being made, the one that we are trying to achieve. Another key word is intermediate compounds. We've seen these before. These are compounds that are formed during the process or during the experiment, but they're not present in the final products. We've previously discussed the conversion of ethene to ethanoic acid and ethene to PVC. Next example, and it's actually part of the next mandatory experiment, is the synthesis of benzoic acid from phenylmethanol. Now, don't run for the hills when you see these diagrams come up in an organic question. We know benzene is there. It's unreactive because even though we're seeing double bonds here, we know there's a pi electron cloud system happening. So that's a very unreactive part of the molecule. The active part is the part I've put the loop around there. And you can see that the active part contains an alcohol group. So that's our methanol part, phenylmethanol. And we're converting that alcohol group into a carboxylic acid group. So that's the part of the molecule we're focusing on. So don't be scared by the fact that there's a benzene ring in it. So we know this is an oxidation reaction, alcohol to carboxylic acid. We're literally adding in an oxygen, or we could say that we're removing 2 hydrogen atoms. The reactant required is potassium permanganate. This is the same oxidizing agent that we saw in all of our redox section of this chapter. The only thing that's changing here is it's not acidified potassium permanganate. This reaction is going to be done under alkaline conditions. So instead of adding a source of H+, we're adding a source of OH- ions instead. The color change that we'll see here, we are going to see a purple color and then to brown before we go to colorless. So this brown color is due to MnO2, which we have actively avoided in every single other experiment we've done, which involved potassium permanganate. This is the only one where we actually want to see that happen. We want to see that brown precipitate. Let's look at the reaction then. We have our phenylmethanol here, which is a colorless liquid before we do anything to it. That's important to note down. We then add our potassium permanganate and we get a purple color as usual with that. We add our base, which is our sodium carbonate, is what we're adding to this to give it its alkaline pH. And when we heat that up, I should really have heat written on the arrow here as well. When we heat that up, the reaction that happens is the alcohol group gets oxidized to the carboxylate group. However, we don't get the carboxylic acid forming straight away. We get the carboxylate salt. We saw this as well when we were making soap. We also have a color change from purple to brown because while this oxidation is happening, the manganese ion is being reduced to form MnO2, and that's the brown precipitate that is formed. The second step of this reaction is we need to convert this carboxylate salt into our carboxylic acid. In order to do that, we add HCl. And what we'll see is the brown color disappears and we see the white crystals of the carboxylic acid, the benzoic acid, being formed. Now, the reason the brown color disappears is because of this reaction down here. We are also adding at this stage some sodium sulfite. And what the sodium sulfite does is it ensures the complete reduction of the manganese ion to Mn2+. Now, the Mn2+ ion is soluble in water, so it will dissolve back into the water and we'll get a colorless solution. So therefore, the only thing that's precipitating out at the end of the reaction is the white benzoic acid crystals. We are then going to cool down this mixture because remember we heated it up, so it's hot. and that will see more of the benzoic acid crystals coming out of the solution. We then have to filter off our crystals and allow them to dry in order to determine how much we have actually produced. On this slide, I've tried to break each step down into its component chemicals and the products that we get from each step. So why did we do a lot of the things that we did? So we used excess potassium permanganate, or we saturated the phenyl methanol with potassium permanganate to ensure the complete oxidation of the alcohol to the carboxylic acid. Sodium carbonate is added to provide the pH that's required for this reaction to occur, which is an alkaline, a higher pH. We heated in a water bath just to increase the rate of reaction. We know rate of reaction increases with temperature. The brown precipitate that we form is MnO2, so manganese dioxide, which is manganese plus 4. When we add the concentrated hydrochloric acid, we're doing this for a couple of reasons. The first is to convert the sodium benzoate to the benzoic acid that we are wanting to produce. So we'll see the white crystals of that forming. And also to help the sodium sulfite reduce the Mn4 plus ions to manganese 2 plus ions. This reaction between the sodium sulfite and the manganese works best in an acidic environment. We then cool the flask in order to maximize the yield of benzoic acid. Benzoic acid will dissolve in hot water, but it's not very soluble in cold water. So by cooling it down, we will force the benzoic acid to be precipitated from the water. We then filter off our crystals and allow them to dry so that when we measure the mass of crystals produced, we are getting the mass of benzoic acid and not any water that might be left over. So recrystallization is done in order to purify a solid or to obtain more satisfactory crystals from an already pure solid. How this is done with benzoic acid. Step 1, we dissolve the crystals in the minimum amount of hot water. Hot water so that we can dissolve the crystals, as they don't dissolve very well in cold water. And the minimum amount because we want this to be a saturated solution, so that when we cool it down, the crystals will be formed. If we used a lot of water, some of the benzoic acid will remain dissolved in the solution. We then do something that we haven't done before. We filter the solution while it's still hot. This ensures that any insoluble impurities are removed. They will remain as the residue in the filter paper, while the benzoic acid that's dissolved in our hot water will pass through the filter paper. We are then going to cool down the solution in order to reform our crystals. As we mentioned before, that benzoic acid has low solubility in cold water. Any other dissolved or soluble impurities won't crystallize because they're going to be present in very, very small amounts. We'll have removed most of it in the previous step. A good thing to remember here is that to ensure the maximum yield of our crystals, you can add a very small pure crystal seed. So you can get a pure sample of benzoic acid and add a little bit, a very small amount of that in, and that will promote the growth of crystals. You can also scratch around inside the flask with a glass rod, which can promote the growth of more crystals again. Or you could evaporate off some of the solvent, so to heat it up to evaporate off the solvent and recool it then again. Finally then, you are going to have to filter the solution in order to separate your liquid from your crystals. So again, we'll use a vacuum filtration using a Buchner funnel. and the crystals will be collected in the filter paper this time, and all the water and any soluble impurities will pass through. Just to ensure that we get the maximum amount of crystals, you can wash them with a little bit of ice water to ensure that any water remaining in there does not have dissolved benzoic acid in it. The final step is drying off the crystals so that we have no liquid left. We often place the filter paper on a clock glass and place it into the oven in school at a low temperature in order to evaporate off any remaining liquid that's left. We can then measure the mass of the crystals and calculate our percentage yield. That's the calculation that goes with this experiment when it comes up. So they may give you an experimental yield, an actual yield. You may have to do some stoichiometry to find out the theoretical yield, and then calculate the percentage yield from there. The final part to this experiment is measuring the melting point of benzoic acid. The reason we do this is because melting point can be a very good measure of the purity of a substance. Oftentimes in a lab they will have a database which will have the melting point range of any number of substances. And the melting point range is the temperatures across which a substance will melt. For example, for benzoic acid, it's between 121 and 122 degrees Celsius. If the substance is impure, it will have a lower value than expected. And also, the more impurities in the substance, the wider the range would be. So this is a very accurate range, 121 to 122. Anything that we make in school will have a lower value and also a slightly wider range. We might see it from 115 to 118 or 19. The key point here is that impure benzoic acid will melt at a lower temperature and over a wider range than if it was pure. Something to note here is you'll note that benzoic acid has a higher melting point than water. Therefore, we won't be able to melt it using our usual ways of melting things like in a water bath. Because of the temperature required, we use something called an aluminium melting point block on top of a hot plate. When we heat up the aluminium block, it allows us to heat things up to a higher temperature than boiling water would. So to get started, we take a melting point tube, also called a capillary tube, which is about the width of your lead in your pencil. It is open on both ends, so we hold one end into the blue flame of the Bunsen burner to melt it shut. We then place the open end and dab it into our sample of crystals in order to force some of the crystals into the melting point tube. Now, if you have very big crystals, you might want to grind them up using a pestle and mortar to make them smaller so that they fit into the capillary tube. But most of the time they're fine as they are. We then turn the melting tube over in order to tap the bottom of it, the closed end of it, on the desk several times, but being gentle because these are very brittle, in order to move the substance from the top of it down towards the bottom. We then place the melting point tube into the aluminium melting point block on top of the hot plate, so you can see that it's in here now. And we record the temperature of the block using a digital thermometer. We watch the crystals carefully through the hole in the block, and we note the temperature when they start to melt, and again once they're completely melted. So you'll see them starting to turn to a liquid. You record the first temperature, and then once they've completely liquefied, you record the finishing temperature. And that gives us our temperature range for the melting point of benzoic acid.